Well, thanks. Yeah, it just happened to work out well. I sort of scheduled an extra day in Europe, and instead of having a nice dinner in Copenhagen, I came here instead. Anyway, it's given you all a chance to have plenty of beer and pizza, so that's good. So this talk's all about sort of some very hot buzzwords: microservices, event sourcing, CQRS, and of course Docker, which is one of the kind of hot technologies. Really, the goal of the talk is just to share with you kind of my experiences of building an application using these sort of kind of new modern technologies, which are quite different from the traditional enterprise Java stack, right? You know, monolith, Java EE, or Spring, or pure Spring with relational databases. So I kind of just started kicking the tires with this technology just kind of a year and a half ago, just to try it out, and I've been super excited with what I discovered. And so my goal is really to share with you my experiences. Put this up a little higher. So anyway, before we get into that, a little bit about me. So I actually got my start in programming way back in the 80s, programming Lisp, building Lisp systems, compilers, runtimes, garbage collectors, frameworks, IDEs, and so on. Back sort of near the end, while artificial intelligence, as it was called back then, was still quite a hot technology. And then eventually ended up programming in Java, and quite a long time ago, 8 years ago, my book Pojos in Action was published, and that was all about building apps with Spring and Hibernate, which back then were these hot new technologies that were transforming enterprise Java development. And then back in 2007, I started tinkering with this obscure thing called Amazon's Elastic Compute Cloud. It was sort of really back in the early days. What was funny, actually, I organized the Oakland Java Users Group, and we had a guy from Google come and talk about APIs for checkout, right? And then the next month, we invited someone from Amazon to come and talk, and we thought it was just going to be APIs for buying books, because obviously that's what Amazon's all about, or was back then. And instead, he actually came and talked about APIs for provisioning servers, and it just blew my mind. And so I actually signed up for the beta program, and I think in early 2007, I got led into that, and I started kicking the tires, and I created an open source project which evolved into a startup called Cloud Foundry. There was a Java PaaS for Amazon EC2. And then this whole cloud computing thing happened, and it was like, wow. And then my company actually got acquired by SpringSource back in 2009, right before SpringSource was acquired by VMware. And there's this great picture from the register of a fish. And I always like to say that it's not drawn to scale, in terms of market cap. Otherwise, I would be fabulously wealthy now. So in fact, Cloud Foundry was much more of a plankton than a fish. It was a tiny, tiny little organization. So after a number of years of VMware, and then SpringSource and VMware Pivotal, kind of left sort of 18 months ago, and working on a startup, which actually is sort of, it's quite buzzwordy compliant. It's actually going to be a platform for building event-driven microservices. And I'm doing a bit of consulting to help people use microservices. I've also created the website microservices.io, which is intended to be a sort of go-to resource, collection of patterns for deciding whether or not you should use microservices, and then sort of how to kind of solve various design problems that arise when you do decide to use microservices. So check it out. There's a bunch more information on these websites. So I've got a fairly comprehensive event sourcing example, both in Scala and Java. I'm going to add other languages in GitHub, plus my blog, and follow me on Twitter and so on. So here's the agenda. So it's kind of like, why build event-driven microservices? What's the big motivation, right? You're going to use microservices, but why make them event-driven? And then I'm going to look into describe event sourcing, which is a specific approach to building event-driven applications, and then just explore various sort of design aspects of the design, and then finish up talking about how all of this gets deployed with Docker. So that's sort of like a kind of bonus feature. Okay, so why build event-driven microservices? And sort of what I'm going to show is kind of sort of a multi-step argument that you know, you start off with microservices and then it leads you down a particular path and you end up having to solve various problems, and the ultimate solution, as I'm going to show to many of those problems, is actually event-driven applications in particular and event sourcing in particular, event-driven applications in general and event sourcing in particular. So if you actually start off at the beginning and think, well, imagine you're going to build an application, like for instance you might work for a bank, right? And apologies for anyone who works for a bank, because I actually don't know what I'm talking about here. But you build an application, you build applications that tend to look like this. So you've got a presentation layer, right? You've got various sort of services, typically dealing with specific functional areas of the application, right? Accounts, transfers, customers, and so on. And you might implement them using Spring and Hibernate, standard technology. But you kind of have this nice modular architecture, right? With layers, with modules, and everything looks quite nice. But then when it's time to actually deploy the application, you tend to just go package it up as a monolith, just this big, potentially massive system, one blob of code that you then deploy on a server such as Tomcat, or if you're in a certain company's WebSphere, etc. And that's serving up HTML to the client, and then there's a SQL database in the background somewhere. And that for me, is a pretty traditional enterprise Java sort of application. And there's good reasons for this, right? It's very simple to develop applications like this. These are, at some level anyway, our tools are oriented towards building web applications. It's pretty simple to test. You can just fire it up, and then you can test the APIs, you can test the UI with Selenium. And then it's also quite simple to deploy as well. You just copy this WAR file into the production environment, drop it into the right directory, and Tomcat will redeploy it, and so on. And also what's nice about this approach, right, is you've got a relational database that gives you a nice, straightforward, ACID programming model, which is what we're all used to. And then if we want to scale up, we can just run multiple copies of this application behind a load balancer, and we're good to go. So it's a nice, straightforward, sort of simple way to build applications. The problem that you run into is that this tends to get painful when you have a large, complex application. You can imagine, you have a team of developers working away, and every day each developer adds so many lines of code to the application. You multiply that by the size of the team, and then do that for some number of years, and you tend to end up with an extremely large amount of code. Some organizations, it could be 1 million lines of code or more. And the trouble is that while this monolithic approach works well for small applications, it really doesn't scale to deal with large code bases. So number one, it tends to be pretty intimidating to developers. You've got this massive amount of code, potentially a complex build system, and finding your way around the code base, figuring out how to implement a particular change correctly tends to be extremely challenging. And in fact, can be actually, more often than not, people don't make the changes correctly. They don't preserve the modularity of the application, and the quality of the design tends to just spiral down. A large monolithic application also tends to be an obstacle to frequent deployments. So if you think about what is state of the art today, right? It's continuous delivery. Whenever a change is made, it gets tested, pushed into production, and you should be able to do that many times a day. The trouble is when you have a large monolithic code base, that's really, you've put all of your eggs into one basket, and so in order to redeploy one small part of that application, you have to deploy the entire thing, which tends to be a sort of scary, risky proposition, which forces you into the direction of extensive testing, often manual, which means that you can only deploy infrequently, which means actually, ironically, it tends to make deployments much riskier. So it sort of gets in the way of continuous deployment. You know, a large monolithic application also overloads your IDE. The larger the code base, slower the IDE is, and the less productive you are. It also tends to overload the app server. You know, a large application can take minutes to start up. And if that's part of your development cycle, that could really slow you down and you end up not being very productive. You know, I've heard about apps taking 20 minutes to start up, right? So if you're developing them, then, you know, there's 8 hours in the day times 3. You can only kind of go around that development cycle 20 times and 24 times, and that's your whole day gone. Anyone actually have that problem, long startup times?
Just 20 minutes.
Yeah. What's the longest, actually? 20 minutes? Longer? Half an hour? Really? How long?
I don't know the production environment, but development environment up to 30 or 40 minutes.
Wow. Yeah. I mean, you know, that kind of thing, it just sort of happens, right? No one plans it. Your application grows and it gets just bigger and slower, and it's a very hard problem to solve. And then it also tends to be a problem, you know, monolithic applications tend to be an obstacle to scaling development as well. You want to break up your engineering organization into teams focused on a particular functional area. Have the UI team work on the UI, the accounts team work on accounts, and so on. And really each team wants to be able to deploy their changes, push their changes into production whenever they're ready to do that. But if it's all going into a monolith, they have to, a lot of communication and coordination is required to roll out changes, which slows everything down. And then you can also have modules with conflicting scaling requirements. You could have a module that's, say, basically a memory-intensive in-memory database, and then you might have another module that's very CPU-intensive, doing some complex calculations. And yet, you know, in a monolithic system, you can't scale those components differently. You can only scale them together, which is suboptimal. And then, you know, lastly, I mean, a big problem with a monolithic application, it basically forces you into this sort of long-term relationship with the technology decisions that you make at the start of the project. You know, if you go back far enough, you might have been using EJB2, right? Or possibly 1, if you can remember back that far. Horrible technologies. But if you've actually built a massive monolithic application using those technologies, it's really difficult to switch to a modern framework because you actually would have to rewrite the entire thing, which tends to be a pretty expensive and risky proposition. And so you end up with a code base that's built using frameworks that no one really wants to do development on. And then plus combine that with the fact that the code base is so large, the code quality tends to be pretty poor, and you end up with just sort of a big ball of mud, basically. And anyone dealing with that today? It's funny, I always like, I don't know if any of you have heard Josh Long speak, but he always likes to say, come on, just admit it, you're amongst friends. So, you know, in fact, I mean, it's just that's a very common sort of painful situation that many of us have sort of found ourselves in over the years, right? So what do you do about it? So a few years ago, came across this book, The Art of Scalability, which was written by some folks who worked at eBay and PayPal. And it was all about scaling engineering organizations, so it wasn't technology specific, sort of scaling the people, the organization, as well as designing scalable architectures. And one of the models that they have in this book is the scale cube, which is a three-dimensional model of scalability. And this was something that really resonated with me. And so one dimension of scalability is x-axis scaling or horizontal duplication application. And the big idea here is that you run multiple copies of your application behind a load balancer, and that improves the availability of your application and lets it deal with an increased load. Then there's also Z-axis scaling or data partitioning. And the big idea here is, once again, you run multiple identical copies of your application, but you use say the primary key of a row to decide which server that row should reside on. Or you could use some attribute of the request, such as the customer ID, to route that request to the appropriate server. So they're both X and Z axis are sort of similar in the sense that you're running multiple copies of the same thing, right? So it would be the same monolithic application. But where it gets really interesting is actually with Y-axis scaling or functional decomposition. And that's quite different. So rather than running identical copies, you break up your app into sort of services by functional area. So you can have the account service, the money transfer service, and so on. And that, to me, is the essence of what microservices are all about. It's not really about building tiny services. It's really about functionally decomposing your application to solve the problems that were listed on a couple of slides ago, to make your life as a developer a lot more pleasant. So if we applied that to this example app, we'd end up with a microservice architecture that would look something like this, where we've got the UI running as one service. We could even split that apart by functional area if need be. And then we'd have an account management service that was responsible for accounts. And we'd also have a money transfer service that was responsible for the business of transferring money between accounts. And each one of those services would have their own database. So they're completely isolated, somewhat, which lets them develop independently. So that's sort of one thing that we might do in our modern application, is actually use the microservice architecture to functionally decompose what would otherwise be a monolith into a set of services. So then another problem we'd actually have to deal with, say, are limitations around databases. So, relational databases have worked really, really well, but sooner or later you typically run into problems of scalability. You can only usually scale a relational database by vertically scaling, and at some point you can't buy a box that's big enough, or you can't afford a box that's big enough. And sort of your relational database architecture doesn't work for you too well. And then another problem you have with a relational database is sometimes you want to build apps that run in multiple data centers with multiple, effectively, masters active simultaneously, one in each data center, and that tends to be kind of difficult to do with a relational database. Schema updates are another issue with relational databases. So in a database like MySQL, adding a column to a table typically touches every single row, which can take a really long time if you have a very big table. You might not have a maintenance window that's long enough to actually do a schema update. Other databases, it's sort of less of a problem. And then, of course, there's always the object relational impedance mismatch, where on the one hand you've got your rich domain model with complex relationships, inheritance, and associations, and it's like, well, how do I map that onto my flat relational model where it's just fixed tables with foreign keys? There's a real kind of conceptual gap there. And then, of course, another problem with relational databases is that they don't do that great a job of handling semi-structured data. You have tables with a fixed number of columns, and so entities that have a variable number of attributes kind of don't fit into the relational model very well. You tend to sort of kind of have to go outside the relational model, have lots of extra columns, or use outer joins, which tend to be very, very inefficient. So it's somewhat of a problem. So some of these problems you can certainly solve by sharding the database. Of course, that's a whole bunch of work. Another problem another way of solving the problem is to use a NoSQL database, which avoids some or all of the problems of relational databases, and for some use cases give you much better performance and much better scalability. So if you want to do text search, you could use Cloud Search hosted by AWS, or you could use Solr, or you could use Elasticsearch. If you're storing a social graph, you could use Neo4j. If you want a highly available, highly distributed database, you could use Cassandra. So there's sort of a variety of NoSQL databases that you can use to address various sort of limitations of a relational model. And you might even use a mixture of databases. If different components based on their data access patterns could use a different kind of database, some relational, some graph, some document-oriented, and so on. But the upshot here, of course, is that you've gone from a single monolithic to a relational database to a whole mix of databases, and you end up with a whole bunch of distributed data management problems. So number one, a simple case, right, where we're storing products in SQL, but then we want to do text search with Elasticsearch, right? How do we keep them in sync? You can't use two-phase commit. That's sort of a problem. Or another common situation is when you're using Cassandra or some other NoSQL database other than MongoDB, you tend to have to build your own index tables, which have to be kept consistent with the main table. So once again, you can't use two-phase commit. How do you keep these two tables synchronized? And then, to go back to the example application with money transfer, you've got accounts in one database, money transfers in another. How do you sort of perform a money transfer that needs to update those two accounts and the money transfer object without having two-phase commit? Even if you're using relational databases, it's sort of considered somewhat unfashionable to use two-phase commit these days, right? So the solution really is to use some kind of event-based architecture. And the big idea, of course, is that when a component changes state, it publishes an event to say that the state has changed, and then other components can subscribe to those events and actually update their own state. So it lets them become consistent with the change that happened in the other service. So with text search, for example, you could end up with an architecture like this. So when the product is updated in MySQL, an event is published, right? Which goes via the message broker into the search service, which can then consume that event and re-index that document. And then likewise with the money transfer service, you can actually use an event-driven workflow to transfer money between two accounts. So it ends up working something like this, right? Like the money transfer is created, an event is published, which then the account service consumes, and that can cause it to update the from account, so the balance changed to 195. It publishes an event to say that the account was debited, which gets consumed by the money transfer service, which records the fact that the from account was debited, publishes another event, which gets consumed by the account service, which can then credit the to account, and then it just, the events get published, and then the transfer is updated to say that it was completed. So we actually managed to end up with consistency, but in an eventual fashion, just by building this event-driven workflow. So that sort of sounds good, right? We'll just use events. But then the challenge is, how do we atomically publish an event whenever a domain object changes, right? Because basically at that point there's now two participants, the data store that you're storing state in, and the message broker that's responsible for publishing events. And once again, you could use two-phase commit here, except that we don't want to use that, right? That's sort of just not a fashionable thing to do, or it's not supported by modern technologies. Another approach, which is what eBay uses, and it's used for a number of years, is that they have an event table in their databases, and when they update state in that database, within that same local transaction, they insert an event into the event table. So kind of with a local transaction, they update state and then queue up this event. And then there's another process that's actually polling the event table and then initiating a transaction on the target database, updating that, recording that the event was processed, committing that transaction, and then deleting the event from the source event table. So there are ways to do it, but it sort of tangles up business logic and event publishing logic, and it only really works if you're using SQL databases. It doesn't really apply with NoSQL. So that's sort of a challenge. All right, so it's kind of like event-driven architectures are great, but then there are actual issues with implementing them, and that's kind of how I ended up with event sourcing, right? So the big idea with event sourcing is for each entity or for each aggregate, to use sort of domain-driven design terminology, you identify the state-changing domain events and define event classes. Right? So for an account, it would be the account was opened with this balance, the account was debited by this amount, an account was credited by this amount. So we explicitly model all of these state-changing events as classes in our system. And then, rather than store the current state of an account, for example, we actually store the sequence of events that have occurred to that entity. And then if we want the current state, we can just replay those events and rebuild the state. So we're sort of changing how we persist states. So rather than saving current state, we persist the events. And why that helps us is that whereas before we had to update state and persist events, which were two things which are hard to do atomically, now we're just persisting events and implicitly publishing them, which is really one thing. And that's fairly straightforward to do in an atomic fashion. But it sort of changes kind of like how we store the data, but also how we implement our domain logic as well. So if you have a quick look at some of the code that I've written. So this is Scala code, and basically there's just the notion of an aggregate that's got an apply event function. The basic or method that actually is a partial function from event to an updated aggregate. So I'm using an immutable domain model here, right? So I'm not doing updates in place. Applying an event gives me a fresh new copy of that object. And then there's the notion of processing commands, which basically takes a command and gives you back a sequence of events. So for the account object, here's sort of the command processing logic. It's basically just mapping input commands to a sequence of events. So if you tell an account to debit itself, it gives you back an event, account debited event. And then you can pass that to apply, which is basically pattern matching against the event and gives you back a modified a copy of the object that's been modified to reflect the state change. So account debited event basically does a copy of the object debiting the balance field. So that's kind of what the domain logic looks like. So it's a little bit different on the surface from how you would typically implement your domain object. So it's sort of very kind of stylized pattern. And the way event requests are handled in this object, in this sort of system, right, is so a request comes in, gets handled by a controller or a service, and you want to modify an aggregate or an entity. So the first thing you have to do is find the events for an entity, right? So we query the event store that's basically our database of events. And then we create a blank account just by calling its default constructor. And then we apply the events to it. So we take the blank and newly constructed account, replay all of the events to reconstruct the current state, and then we process the command, which gives us back some new events, which then get persisted in the database. So it's very event-centric flow. And what gets interesting is that not only is the event store saving the events, so acting as a database of events, so you can find them and you can add new ones, but on the other side of it, you can have subscribers that are saying, I'm interested in events of this type, right? So this could be other services that sort of are participating in this workflow that need to maintain their consistency when state changes happen. And then those subscribers get notified of these events that have been getting saved, and then they can either update another aggregate, which would then triggers more events. And so you could think of that happening when you create the money transfer. That triggers the update of the from account, which triggers the update of the money transfer. So you end up with this sort of chain. And then you can also update views as well. So this is kind of the CQRS part of it that I'm going to talk about later. So basically it's like whenever state changes, you save the event in the event store, and then that consumers of those events can actually do their own updates of other aggregates or update views, which is sort of storing a denormalized copy of the world. And then sort of one extra feature here is that we might think, well, I've got an account, it's been open for 10 years. That's an awful lot of debits and credits to replay in order to tell me what my current balance is, right? So the solution to that is to periodically take snapshots of your entities. So if there's a large number of events, you take the snapshot that basically encapsulates the state up until that point. And then when you want to retrieve the events for an entity, you first go get the most recent snapshot, and then you just get the events that have occurred since that snapshot, and then you can just replay those. So you never have to go all the way back in time. So that's kind of a useful optimization. The event store API itself kind of looks like this, where you can save the events for a new entity, update the events for an existing entity, and then there's some find methods, and then at the bottom there's also a subscribe method that consumers use to subscribe to interesting events that occur. And there's various ways of implementing it. Like I think some folks have implemented, basically they implement their own event store, right? I think that's what you're doing. Greg Young, who's been sort of kind of basically invented event sourcing and CQRS, actually has his own commercial event store as well. And I'm also working on one as well. I think it's kind of a super interesting technology. So talk to me about it. So there's a whole bunch of benefits to doing event sourcing, sort of both kind of at the business requirements level, but then there's also a bunch of technical benefits as well. So if you think about it, every change that's ever made to an entity has to result in an event. So we get this built-in audit log that's 100% reliable. We don't, whereas the traditional approach of, well, we implement our domain logic and then we add some auditing logic in there as well, which we kind of have to remember to do. We have to remember to keep it consistent. It's kind of somewhat flaky. Also, this approach enables temporal queries, right? Because we've got the history of each domain object, we can actually ask the question, what was the state of this entity at this point back in time? So we've got a complete historical record, which can be useful in some domains. If you think about modern architectures, they tend to have like a machine learning predictive analytics capability off to the side, right? That's sort of observing user behavior and making predictions, like showing them cat pictures that are more likely to engage, right? You don't have cat pictures in Germany? They're huge, huge in America. People, mostly people spend their time on Facebook looking at cat pictures. What do people post pictures of on Facebook here? Yeah. So, but it's very funny actually. Like the folks at Yahoo, like I don't want to pick on Yahoo, but they love to give talks on their super sophisticated machine learning predictive analytics capability. Yeah, if you go to the home page, it's the same old useless news stories about Kim Kardashian and pictures and stuff like that. But anyway, that tends to be a big component of modern applications, right? Having some machine learning capabilities. And so this stream of events, which is representative of user behavior, can be naturally fed into a machine learning component. It also preserves the history of what's gone on in your system. So if you want to implement a requirement as if it had been there from the from some point in the past, you've actually got all the data that you can then sort of feed into that new component, and it can just sort of generate state as if it had been there from the beginning. So it kind of gives you flexibility in implementing unanticipated requirements, which is quite good. So there's a bunch of business benefits there. And then, of course, there's a few technical ones, right? Like, it solves a whole bunch of data consistency issues between all these different databases that we have in the system, right? It lets you atomically save and update state and publish events, and then subscribers can consume those events and implement some eventually consistent mechanism. So that's quite good. And then it also solves this OR mapping problem. So all we're ever persisting are events which tend to have a pretty simple structure, right? So we can just persist those. They're easily sort of mapped, easily serialized in JSON format or whatever. And the domain object, the domain objects that the events are being generated by can be arbitrarily complex, but we never have to persist those. So, so we've kind of just simplified a lot of the sort of OR mapping kind of problem. There obviously are some drawbacks, right? Number one, this is very weird and unfamiliar, right? Like, we're all used to just like persisting state. And so the notion of writing this event-centric business logic takes somewhat getting used to. I mean, you're saying the same thing, right? It takes people a day or a week to get their heads around it. And then also there's a risk that your event can be like kind of like the historical record of all of your bad design decisions. Because, these events, unlike a schema, right? Sort of a current, when you're storing the current state, you've got a schema. You can always apply database migrations to it to change the schema to improve it, right? Whereas these events tend to just be an immutable data that you can never go back and change, right? And so in theory, you can actually make some bad decisions about the design of your events, and you're kind of stuck with it forever. In reality, what's actually quite nice though is that typically the events really correspond to things that happen in the problem domain, right? So they're just sort of modeling more of the real world rather than the invented world of sort of technology. And so they tend to be reasonably simple and also reasonably stable as well. So this is, I think, a relatively rare problem. A more interesting problem, actually, though, is whenever you're building an event-oriented or message-oriented system, you tend to have to deal with duplicate events, duplicate messages, right? Because, like implementing a message broker that guarantees exactly one's message delivery behavior is really complex and expensive. And so you tend to have message brokers that give you at least once semantics. So there tends to be the possibility that you will see the same event twice. Sometimes that doesn't matter, right? Because applying the event can be idempotent, and so it doesn't matter how many times you see it. But if it's, say, a debit event or a credit event where you're adding to or subtracting from some total, that is not an idempotent operation. And so but that, in those scenarios, you actually have to implement duplicate detection in order to know when you've seen an event before and you can throw it away. I mean, what's nice is that's actually reasonably straightforward because you can just keep track of the last seen event ID, and if the event, then when you get an event that is not later, you can just throw it away, assume that it's a duplicate. So even though it's a problem, it tends to have a pretty straightforward solution. You know, another interesting problem is because now things are not happening atomically, there's the risk of seeing inconsistent data. So like one scenario, right, is that you update some entity, so that actually updates the entity in the event store, and then you do a read. But the read actually comes from a view table that I'm going to talk about in a minute that is updated by a consumer of events coming from the event store. And of course there's always a replication lag, so you do your write and then you do a read, and the read is actually the stale data, it hasn't been updated yet. Normally we're sort of the speed of like UIs, human speed, that's not really a problem. But I've noticed that in tests, right, where tests tend to, they sort of run at machine speed. There's no think time involved. And so that actually, I've actually had to write tests that kind of are very tolerant of eventually consistent data, and so instead of making an assertion and failing immediately, they actually loop, if the assertion is not satisfied, they actually sleep and retry, and some number of times until the state change has occurred. So that's a little tricky, but it's funny, we've all grown up thinking things must be ACID, but almost always you can actually kind of break it down into an eventually consistent workflow, and it works just fine. Even banks, I'm told, work that way as well. And the great example is eBay, the auction site. So even though they're dealing with money, they actually have partitioned relational databases, and so there is this eventually consistent workflow to update them, and that works okay. Then another drawback of event sourcing is just the idea that the event store only supports primary key-based lookup to find the events for this entity. So it doesn't support joins or any of the richer kind of query constructs that we're used to. And that's actually where CQRS comes into play, and I'm going to talk more about that later. All right, so that's sort of event sourcing. So that, what do microservices look like when you build them using event sourcing? So sort of at a high level, each microservice, which in domain-driven design terms corresponds to a bounded context, whatever that means. It's a very sort of in itself, it's a vague term, right? Some functional area of your application. Invariably, so what that translates into is that each microservice implements one or more, typically more, aggregates or entities, right? So I'm just drawing one in here. So you can think of the building blocks that are for, the basic unit of what you build microservices out of is actually an aggregate, and there will actually be several aggregates in each microservice. And then there are actually adapters that take requests coming in from the outside world, say over HTTP, or possibly from some other message broker, RabbitMQ or JMS, whatever you're used to, turns that into a command, which then gets fed into the aggregate, which then spits out events. So the command causes a state change, which then spits out events, which then get persisted in the event store. But then at the same time, the aggregate is subscribing to events that are coming from the event store and turning them into commands as well. So commands are coming in from two places: external requests and in response to events that are being generated by other microservices. So that's kind of the big picture of how all of this works. So the key thing is events are ending up in the event store. I mean, how that looks like at the code level, so here's a Spring MVC controller that's handling a post to create a money transfer. So it's written in Scala. And it's just invoking the money transfer service and then generating a response. And there's sort of a bit of boilerplate in here because this is written in an asynchronous style, using Scala futures and Spring MVC deferred result objects. So that's why there's a for loop in there, even though it's really just working on a Scala future. And then the actual money transfer service in the example code, the Scala version, looks like this. And I've implemented this tiny little domain-specific language that kind of hides all of the boilerplate with interacting with the event store. So this one line, new entity money transfer, says go create brand new entity of type money transfer, and then tell it to process this command. That's what the arrow does. And so under the covers, it's actually creating the money transfer object, so invoking its default constructor, invoking process command on it, which results in a sequence of events, applies those events to the entity, and then also persists those events in the event store. So that's sort of implementing that kind of request handling workflow described a while back. But that's all kind of just neatly hidden away using just this sort of arrow notation, which is kind of one of the cool features of Scala. And then the actual money transfer object kind of is a money transfer, and it has a process command and an apply event. And then there's various event classes. One to say it's been created, one to say that a debit has been recorded, another one to say that the credit has been recorded and that the transfer is complete, and so on. And then, here's an event handler. So here's how you write the code that's subscribing to an event that's coming from the event store. So in this case, the money transfer wants to record the fact that the from account had been debited. And so once again, I have a little DSL that says, go find the existing entity whose ID is this, so the transaction ID from the event, and have it process the record debit command. So under the covers, that's actually loading the money transfer aggregate from the event store, processing the command, applying the event, and then saving the new event back in the database. And if you go look at the Java versions of this, it's similar, except that it takes like 10 times as much code. It was really funny, actually, because originally it was a Scala example, and then it was Scala and Spring, and then I figured out that the intersection of people who like Scala and like Spring were relatively small. There's something about the Scala community where you have to say how much you hate Spring. I mean, I'm a big fan of Scala, I'm a big fan of Spring. So I actually rewrote the code. So I actually rewrote the code in Java, and that was just so tedious. It was like just blew up, in terms of just amount of boilerplate getters and setters and all of that. But anyway, so that if you go to the event sourcing example in my GitHub repo, you can kind of dive into both those examples. So that's kind of what sort of the request handling code and sort of the event handling code looks like. So the other part of this is, well, what about queries, right? So, earlier I mentioned that one big limitation of event stores is that they're only primary key-based active retrieval of events, right? You can't do joins and anything like that. Yet if you think about, things we need to do in our applications, we actually need to query in a way that sort of implies joins. So we might want to display an account, show the debits and credits, but also show the actual transactions, right? Like the fact that the money was transferred out of this account into some other account, or was transferred out of some other account into this one. And what that actually kind of conceptually means doing is effectively doing a join between account and the money transfers, right? You know, if you imagine doing that in SQL, you sort of have some kind of outer join thing, right? Because it's either, you know, to find the money transfers for an account, it's either the from account or it's the to account. And so, but, you know, how do we do this with an event store? Because there's no possibility of joins. And that's where this pattern command query responsibility separation comes into play. And the big idea here is that rather than have a component of your application handle both commands, handle both the updates and the queries, we actually separate it out. So we have a command side of our application, which is purely for dealing with updates. And that's exactly what I've been talking about up until this point. And then we have a separate component in our application that's responsible for handling queries. And, you know, as the name suggests, we're sort of separating responsibilities, separating concerns, which actually ends up simplifying the command side because it never has to think about queries, right? It's purely primary key-based access, and the logic there is entirely to do with handling commands, which tends to be somewhat simpler than the query side. Then what's interesting with the query side is that we could actually have multiple sort of different views of the data designed to optimally support all of the different kinds of queries that we need to handle. And the way that it all gets tied together, right, is so the command side, whenever it, by virtue of updating aggregates, always publishes saves event into the event store. And then the query side can subscribe to those events and update its view of the world, right? Update one or more denormalized views of the data. So we end up with kind of these view side microservices or query side microservices. So we have, say, a view table, which could be Mongo, could be Neo4j, could be Elasticsearch, Cloud Search, could even be a relational database as well. Then we have a microservice that's responsible for updating it. So whenever the relevant events are published by the event store, the microservice consumes those events and updates the view. And then the queries that are handled by the HTTP GET can be handled by another microservice that's basically just querying the events, querying the view store. So if it's Elasticsearch, it will be takes the HTTP GET, turns it into a text search to find the documents that have been published by the view updata service. Like in the code I've been using Cloud. Actually, I've been using either DynamoDB for most of the queries, or I've been using Cloud Search for the text-oriented sort of text search queries. And then for this particular example, I'm actually using MongoDB. Basically, for each account, I have a Mongo document that's storing all of the debits and credits corresponding to the debit and credit events that have occurred on that account. Like you could trim that list to keep just the last 10 days. And then it's also storing all of the money transfers that impact that account, either transfer money in or transfer money out. So if you think about a debit event, it doesn't say where the money is going to, or a credit event, it's not saying where the money is coming from. So by storing both the debits and credits, as well as the corresponding transfers, you get to see where the money is coming from and going to. So it's sort of a very denormalized representation of the data, but the beauty is that with Mongo, you can just retrieve this quite complex document with just a single primary key lookup, and with Mongo, it's pretty efficient. And then the actual handler, just kind of not showing all the code, but it's basically subscribing to the account opened, credited, and debited event. And then it's also subscribing to the money transfer created event as well. And then just, I'm using Spring Data to actually update the corresponding document. And then as I mentioned, so in my app I'm actually using Cloud Search to do sort of text search. Other folks can use Elasticsearch. And then for some of the views, I'm just using DynamoDB. So it's just sort of a hosted, and that's great for primary key retrieval of data. So I got views sort of corresponding to entities. Oh, it's okay. It's all right. It's actually okay to be offline for a little while. Actually, on the way here, the flight from San Francisco to Copenhagen did not have Wi-Fi. So that was kind of rough. Nor did it seem to have on-demand movies either. Alright, so anyway, so that's sort of CQRS, right? So we kind of have these separate views for handling queries. And, you know, a bunch of benefits to using that, right? So number one, you know, it's kind of a necessary part of an event source system. It's sort of, because you kind of need sort of more complex views than just kind of primary key lookup. And it does separate out concerns, which can simplify things. And then you can have multiple views. So you could, if you had graph-oriented queries, right? You could take the data, take the stream of events, update Neo4j, and also update Mongo. And then Neo4j handles the graph-oriented queries, and Mongo handles the document-oriented queries. And so you get like this super efficient implementation of the queries at the expense of sort of having more denormalized copies of the data. But because you've got this nice stream of events, it's really easy to keep the denormalized copies up to date. So you get, you know, good scalability and performance. Downside, of course, is a whole bunch of complexity and maybe code duplication from the command side, and also this whole notion of replication lag. And so, hence, you know, if you do an update and then go query the corresponding view, that update might have not been applied yet. So you're going to see slightly out-of-date data. So, you know, interestingly, one way of handling that in the UI is to simply, so that, you know, you have some Ajax or JavaScript app running in the browser, it can send the request to the server, which is going to accept the request. And then you just update the UI right away, and then you're not and don't actually bother kind of going and retrieving the updated view. You can just sort of update it in the browser under the assumption that by the time the user navigates away and navigates back to that page, that the replication will have happened. And that seems to work reasonably well most of the time. Anyway, so that's sort of event sourcing and CQRS. And I sort of want to change gears and just talk briefly about how all of this stuff gets deployed. So if you look at the application architecture, it's sort of something like this, right? Where I actually have an API gateway that's implemented in Node.js. So that sort of provides a single entry point into all of these various services, which themselves are all implemented using Scala and Spring Boot. And then hanging off sort of the other side of the event store is an indexer that when entities change is using Cloud Search to store the data for a text search. And then there's also an event archiver that's actually just sort of doing a backup of all of the events into S3. And kind of both for backups, and it's also, the data is there and could be processed by Hadoop or by Spark or the like. And then sort of the reason why I'm using Spring Boot is that it's like, kind of makes it really straightforward to create these sort of standalone production-ready microservices, right? Like just out of the box, you get all this convention over configuration kind of mechanism applied, so your actual Spring Bean configuration is really, really simple. Plus, you effectively end up with a skeleton of an application. It automatically like externalizes configuration. So one of the things I'm doing is I set environment variables to tell my app to, you know, where the host IP and port of the event store. right? And Spring Boot automatically picks that up, which is really nice. It also gives you built-in health checks as well. So all of my services have a /health URL that reports their status, and I didn't have to write any code for that. And it also integrates nicely with CodaHail metrics as well. And I just had to write a little bit of code to periodically publish those metrics to AWS CloudWatch. And then the other nice thing is that it takes your application, and instead of building a WAR file that you still need to have Tomcat to run it on, it actually publishes a jar with Tomcat or Jetty embedded within it. So basically you can run your app with java-jar file name. That sort of just makes the whole microservice deployment thing really, really straightforward without kind of having to do a whole lot yourself. And then the whole build mechanism is I'm using Jenkins, and so that actually kind of is a multi-step pipeline. So I build and test the microservice in the usual kind of way. It's like a little too much beer, maybe. Yeah. And then I build and test a Docker image. So each of my microservices gets packaged up as a Docker image. And then the final step is once the test is passed, that Docker image gets pushed to a registry. Basically a repository of all of these built Docker images. And so there's like one pipeline per microservice. So who here is using Docker, by the way? Anyone? Yeah. It's real interesting. It's got, there's a bunch of things about it that I quite like. So one of them actually is that building a Docker image takes like 5 seconds for me. So which it's like blindingly fast, right? So that's quite, you compare it with how long it takes to build an EC2 AMI, for example, which is more like minutes. But all it's really doing is actually copying the WAR file into a base image that's already got Java packaged into it. Then I actually, in my pipeline, I have a smoke test where the test actually uses the REST API provided by the Docker daemon to actually create a container from that image and just pings the health URL, just to make sure that that image is not broken in some brain-dead fashion. It's just like it hasn't been misconfigured or anything like that. And then the final step of the pipeline is to publish the image. So I'm doing kind of basically a Docker push that actually pushes the image to a registry that's actually running on localhost, but the registry is backed by S3. So each of my EC2 instances has a registry running on it that's pointing at an S3 bucket. And so my images end up in S3. And this step, it's actually surprisingly takes 25 seconds, so it's actually longer to build than it is to push it up. And then what's really interesting is the actual CI environment is actually running in is actually Docker-based as well. So both Jenkins and Artifactory are running inside Docker containers, and they're building Docker containers. It's like Inception in a way. And the only little wrinkle here is because containers can you can start and stop them, and their version of the file system basically is ephemeral. I actually have an EBS volume that's got Jenkins home and Gradle home and Artifactory home on it, and then those directories are mapped into the container file system, so they're basically durable. So I can stop and start stop, delete, recreate those containers, and they just have they just use what's in the files, the Jenkins and Gradle and Artifactory home directories. And then actually updating the production environment, I've got a really sophisticated runtime system, which basically is a Python script that compares what's running with what's been built inside Jenkins using the Jenkins REST API, and it just sees what's out of date and generates a shell script consisting of basically Docker commands to cool down the latest version, stop the current version, and run the new version. So right now it's really simple because I'm just running on a single EC2 instance. Now when it's time to scale up, that's kind of like, and I want to have multiple instances, that's kind of when you run into the kind of the complexities of Docker, right? Like if you think about deploying AMIs on EC2, you've got all that automatic mechanism in place, auto-scaling groups, elastic load balancers, and the like. Yeah, if you use Docker, you're kind of on your own, and then you have to use Docker Cluster Manager, which is all very new. You know, the paint is still not dry on those technologies yet. And there's a lot of complexity that if you want to actually install one, install them and get them up and running is kind of complicated. And so one day I'm going to have to deal with this, and sort of not looking forward to it. So that's pretty much my talk. So sort of in summary, right, event sourcing solves some key data consistency problems with both microservices and also partitioned SQL and NoSQL databases, right? Lets you maintain consistency easily across multiple databases. And then, of course, if you use event sourcing, you need to use CQRS to implement the views for queries. Spring Boot is a great way to package up your microservices, and then great way to sort of foundation for building the microservices. And Docker is a very appealing way of packaging them up, though there are some downsides. So anyway, that's my talk. Thank you for listening, and happily take questions at this point.
When a command comes in and it needs to check the state, would you typically check the aggregate or the read model?
Oh, that's a really good question. So when a command comes in and it needs to check the state, do you check the read model or the aggregate? No, so commands purely exist within the command side, and so you always check the aggregate. So because the read, it's like the command side is guaranteed up to date, whereas the read side is, or query side is, eventually up to date. That was, yeah.
I have a question about this money transfer example, because I have something like 1,000 euros and I give 700 to you and 700 to some other person. Depends on the order of the event. So the first one gets it, the second one not. And how can you guarantee the order of events without having the event store a global barrier for the whole system where everything's serialized?
Yeah, so that's a really interesting question. Sort of like, how do you guarantee ordering? And so in reality, what happens is the updates to a given aggregate are serialized. So for instance, if two requests came in simultaneously for the same aggregate, right? Like they both loaded that aggregate and then tried to save events for that aggregate, one of them, the first one to do it would succeed, but then the second one would actually fail because of basically an optimistic locking failure. I didn't mention that in the talk. So it's basically our aggregates have a version number, and so when you read, you get that version number, and then when you do the save of the new events, you pass back in that version number that's then checked against the current state. So you get you're getting serializability at the aggregate level. And that was a question somewhere. Yeah.
I was wondering, on your model you showed that the events are persisted in S3, and then there is also the actual processing, for example, into the cloud search. So why don't you power the cloud search generation from the S3 storage? For example, to be able to reprocess a programming error that may have occurred. Because if you take it directly from the queue, you might run into the problem that well, it might not be available, and then you have to rebuild it, and then you incur large downtime.
Okay, yeah. So it's sort of like, well, there's an event archiver that's saving in S3, and then there's the cloud search indexer that's reading from the queue. And why doesn't it read from S3? So one reason that you want to have the indexer in times of like when it's operating normally, reading from the, well, subscribing to the event store, is that it's basically kind of up-to-date real time, right? Whereas until very recently, trying to do anything kind of dynamically with S3 was a little challenging, right? Like in terms of, you know, I guess you could periodically poll a bucket to see what new content has arrived, right? But interestingly, now with like with the AWS Lambda capability, you could actually take an event-driven approach so that when something gets dropped into S3, a Lambda gets invoked, which could invoke Cloud Search. And so you could maybe do it that way, though I'd sort of argue that it's somewhat roundabout. And so if a view needs to consume events, I think it's much more direct, much more straightforward just for it to subscribe to the event store. But then, on the other hand, if you ever need to rebuild a view, one strategy actually is basically to run a kind of like big data batch job against the S3 bucket, which has all of the events from the beginning of time, and using Hadoop or Apache Spark, you could actually rebuild the views at that point. But that's sort of like kind of the bulk, you know, batch-oriented way of view rebuilding, whereas keeping a view up to date, you should simply subscribe to the event store.
So this concept of Lambda architecture would then say do both.
Yeah, except, so yeah, could Lambda save them both? Except that if anything ever goes wrong with the Lambda mechanism, Lambda doesn't give you a way of replaying, right? Like it's only, whenever something gets dropped into the S3 bucket, a Lambda will get invoked.
I didn't mean the AWS Lambda, it's the...
Oh, that other Lambda thing. Yeah, I mean, the whole Lambda architecture from sort of big data Lambda architecture. I mean, yeah, there's some similarities here. I mean, it's sort of, in some ways, I mean, it's kind of Lambda-like, right? So you could periodically, at some points, recreate the views by doing a batch job, and then the real-time stream from the event store keeps the views up to date. So in that way, it's kind of like the Lambda architecture.
You don't seem to like that so much. Could you elaborate on
that? I guess I just view it as similar. I don't know if I view it as exactly the same thing. But there's definite similarities. Actually, yeah.
Do you find that the change in architecture influences your REST API? So, for example, you might have a function with CRUD create that kind of gives you a view state back, but if in this new world where it's showing command, we have two options. We can say, yeah, that command's been queued up and we let you know with a ticket, or you could block and wait for an event that corresponds to that command and then give back the data.
Yeah, so does this architecture change the REST sort of design of the REST API? Now, interestingly, the commands are not queued up; they're actually executed immediately. So, you know, the post request comes in, you actually execute the command as part of, while processing the HTTP request. I mean, I do think there are some other sort of CQRS implementations that queue commands as well as queue events, but in this system I've built, commands are executed immediately. And so the response to the post could actually contain some, like a representation that's derived from the aggregate, showing a sort of up-to-date state, if need be.
Yeah, I suppose in some cases the user might be expecting something that might be similar to their view that they query.
Yeah. So it's, yeah, effectively it's, so I suppose some of the code I've written, I mean, the view is not that different. So when I create an entity, it would normally go to this, you know, you create an entity, then it basically redirects to a page that shows that newly created entity. And the code that I've written so far, that page basically is showing a pretty simple view of the entity. So what you get back from the command side is pretty much what you see on the view side anyway. It's not doing anything more complicated. But I can imagine more complex scenarios where you kind of have to go to the view side, in which case, like, the post request could actually say, okay, I've updated the entity and the expected version number is this, and the new version number is this. And then you could periodically poll the view side until you get the version number you want. I mean, that's a possibility. Yeah.
Yeah, follow-up question on what you just said. So are you saying that when like for example, a command would come in, you directly manipulate the aggregate? Or do you then send a command through the message queue?
So it's actually the former. So the command is processed there and then, synchronously. As opposed to, as I said, I think there are some systems where the command goes onto a message bus that gets routed to an aggregate. And, yeah, what I've built does not work that way. So basically, literally, HTTP request comes in, load the aggregate from the database, process the command, save the events back, and then the HTTP response is generated. Yeah.
How do you ensure that messages are not lost? Like, how does the message bus know that a consumer is going to consume something, but it's, for example, down during...
oh, yeah. Yeah, excellent question. So every subscription has an ID. Yep. Yeah, a unique ID, and so the actual subscription mechanism basically gives you... basically durable subscriptions. So events basically get queued up until the subscriber connects, and then it gets caught up. Way in the back.
What do you think of Kafka and integrating it into this architecture?
Oh yeah, that's a really funny question. Actually, my event store is actually one of the components I use is Kafka. So Kafka is awesome.
It is.
Yeah.
Another question. Do you make a distinction between events that you actually push to the bus versus some data that might stay local inside of the microservice? So to speak, stuff that gets consumed by other services goes to the bus, the rest stays local inside of its own store?
You know, yeah, kind of the notion that you can have some state that's sort of private versus the event stuff that's sort of for global well, that's to be shared is an interesting one. So currently, there is no concept of like local state. So everything, so any notion of persistence really in the command side actually goes to the goes via the event store. The challenge that you would run into is if you had, say, sake of argument, MySQL database, right? Some kind of local state store. The problem you then have recreated for yourself is actually atomically updating state and publishing events again. And so I don't do that for that reason. But it's an interesting concept, though sort of hard to implement. Yeah, in the back.
How do you implement a failover mechanism that if an event goes in and gets validated at some endpoint service and there is something going wrong and there are a lot of services which are involved in this event and there has been a lot of changes and now I have to roll back them. So how can you implement a mechanism to catch all of them?
So, interesting question. So the only failure that kind of I think of in the system is that a consumer of an event can fail to process that event. For instance, it wants to, so say some consumer wants to read an event and update DynamoDB. And so in that scenario, if DynamoDB is down, that consumer basically sort of stops at that point. I mean, it can actually do sort of retries and that kind of thing, but it's like right now, if the event handler fails, then that consumer basically stops at that point.
I think what he's trying to say is, imagine if you wanted to update 3 different entities within DynamoDB, or documents, I think.
Yeah.
So let's say if only 2 of them went through and 1 of them didn't go through, and that job wasn't ticked off as completed, what would happen if that operation is not idle points?
Yeah, so, well, it depends sort of why it's failing, right? Because if it's failing because there's some kind of temporary networking glitch and DynamoDB is inaccessible, or you've temporarily exceeded your quota, your provisioned write throughput, then one option is that just it gets suspended temporarily and then retried at a later date in the future.
May I try answering the question?
Sure.
I went to Greg Young's workshop, so my answer would be, this shouldn't happen. So if your aggregate actually publishes an event and stores it in the event store, then this is your transactional boundary. So this happened. An event is always in the past tense. So when account created, this event happened. If it's stored in the event store, you can't change it. There can't be any validation after that point in time that tries to change what happened. This is a fact in history of your system that's recorded, and after that you can't change it. If a consumer of that event has further actions based on that, he might retry or fail or do something else, but the transactional boundary is after your aggregate has published those events. Not doing around and having two-phase commit-like things. If this one then fails over there, I have to roll back something. This does not happen. Events published to the event store are a fact, and an effect of in time that happened, and you can't change it afterwards. So this shouldn't happen, and then this would be a design issue. Does it make sense?
That is a really good answer. Okay. Yeah. Thank you. obviously failure at the business level, right? Like you try and debit, you know, like even with a money transfer, right? You could actually debit one account, and then when you try and credit the target account, that could actually fail because the target account is now closed, right? And then interestingly, so that could generate an error that then tries to undo the debit. And then in theory, the from account could be closed as well. I mean, you know, that sort of that is possible, right? In which case the system just goes and then it actually, you know, that money transfer would end up in a help, I need human intervention state, right? And then someone would have to go in and well, the bank would just take the money, yeah. Yeah. No offense to anyone who works for a bank. But then, you know, then on top of that, there's just sort of transient, system-y kinds of things that can temporarily mean something just stops working for a while. Yeah.
So, where are the downsides and where are the sweet spots? Do we have any experience for which kind of products is better suited?
Yeah, so... Well, yeah, obviously, I mean, I don't have a very precise answer to it, but it's an excellent question. It's like, when does event sourcing fit, and when does it not? And so obviously, one aspect of event sourcing is that it's for sort of one entity at a time oriented business logic, right? Where you kind of want to update one entity or a few entities. And you're doing primary key access, right? Whereas if you were sort of doing some sort of SQL-like blind updates, you know, employee set salary times, you know, salary equals salary times 1.1 type stuff, then that's not a good fit for this sort of domain-oriented business logic, right? So that's sort of, that's definitely kind of a requirement that it's like, well, the business logic, the business logic is complex enough to require a domain model. The request response, the request handling is very much entity oriented or a few entities at a time. And also, you know, then you have to have some of the, so, you know, typically you're going to have multiple databases that need to be kept in sync, or, you know, if you think about some of the technical or the business benefits actually match the requirements of your application. Like, oh, I need 100% accurate audit log, right? I think that's a good motivation for using event sourcing. Or I've got multiple databases that need to be kept in sync, and I can't use two-phase commit. So there's sort of a whole bunch of use cases that, you know, that seem like it generally fits in. And then there's other ones like batch updates where it clearly doesn't. I don't know if anyone else has anything to say on that. Yeah?
You mentioned monolith, right? Source model inside the monolith, try to get an update aggregate with the old logic, and then build a microservice on it. Then break down iteratively the monolith.
Yeah, so you're sort of saying you could use this for migrating from a monolith?
Yeah.
Yeah. Yeah, I mean, sort of how, you know, breaking apart a monolithic application is always sort of a challenge, right? Because you really want to, like, figure out which chunk of code embedded in the monolith is a good candidate for being, like, extracted out and turned into a standalone service, and then you kind of have to write some glue code to tie the monolithic code base back in with the pristine service. And, like, I don't know if that's, and some kinds of events, you kind of nice to have events flowing back and forth, right? So certainly if the microservice is publishing an event through event sourcing, those events can then drive updates back in the monolith to keep the monolithic database in sync with the microservice database. Getting events out of the monolith can be challenging. You might have to use like database triggers, for instance. So, yeah.
What are your thoughts on shared code between the microservices?
You know, so definitely some library code is quite. I mean, it makes sense to share, right? Otherwise, you're just duplicating stuff. But sort of once you kind of start heading up the stack into sort of more domain stuff, then you could potentially run into problems, right? Where, you know, you want your microservices to be reasonably standalone and decoupled from one another. And sometimes, I mean, code sharing could introduce coupling, right? You kind of update one, you got to update the other. So, it kind of depends. I mean, do you have any specific examples?
No, it's just that some people are absolute purists on it, and they say no code sharing at all.
Yeah, I mean, you got to be afraid of the purists. Should always be afraid of them. Well, that's sort of a purist statement in itself. Yeah.
Would you use DynamoDB as an event store?
Pardon me?
Would you use DynamoDB as an event store?
It's funny you should say that, because not only is Kafka awesome technology, but DynamoDB is good too. So yeah, I mean, the event store that I'm building on, I mean, that lets you plug in different, well, first off, an event storage engine, and sort of the messaging bus as well. And so I'm actually using DynamoDB to store events. Mostly because I like the operational side of DynamoDB, right, in the sense that it's just sort of this service that they provide. You just you know, turn a dial, so to speak, to actually select the read and write capacity, and they just take care of everything. So it's a little more kind of automatic than, say, just using RDS, for example. Really, you know, it's the instance-oriented relational database service. Yeah?
You said something about we have bad design decisions in events, but this is still data we maybe have to show it to the user. So we create this data, or we have migration inside the code, or how do you think about that?
Will you say you want to show the events to the user?
Yeah, or something like that, it's data. There's a transfer object. I change the right, okay, I have another transfer model. So what happens with the existing events?
Oh, yeah. So in theory, so like, I mean, the events can change in various ways, right? I mean, easy changes is you could add extra fields to your event, right? And so that means that events published, older events are missing that field, and later events have that field. So you tend to have to just make sure that your code supplies the default value for that event, right?
So not renaming the type or something like that.
Well, yeah. That's the simple case is adding an attribute, and then you just have to handle that missing attribute, supply a default value, which is not really any different to adding a column to a table and specifying a default value. You know, the really elaborate case, sort of the tricky case, is when you decide to change the name of the event, right? In which case your aggregate might actually have to support the old event and also the new event, right? So there's sort of like migration code, you know, in your system, but it's actually part of the aggregate, or maybe you could do some pre-processing of the event to map it into the new form.
You would create copies of this in the new form.
Yeah, so it could be quite messy, though. I mean, though on the other hand, what I'd like to say is that the events tend to sort of mirror the problem domain, and I think often the language that, say, domain experts use in a given domain tends to be pretty stable, right? Like we as developers, we make up names all the time, right? Just based on whim, whereas domain experts have their vocabulary, and events tend to be reflective of that vocabulary. Well, I can keep talking, but
Yes,
I guess I have
No.
to stop. So I'm like waking up now.
Do you want to continue Q&A in the big format, or do we break up into more smaller groups and just come up and fire your questions off? First, yeah. Small feedback, not if you want to keep the big round for Q&A. Oh, so then I would say thank you very much, and you're available.
Oh yeah, I'm just gonna be here. So yeah, please like follow me on Twitter or shoot me an email. I'd love to stay in touch. So yes, thank you.